Hey guys, I'm Siu Chen. I'm a junior student in material science and engineering. So this summer I participated in the summer research program and did a research with Professor Karasu Thornton, mainly doing computational material science. Computational material science uses computers to simulate the behavior of materials. It is now becoming a more and more important part of material science. This method saves lots of money and time compared with traditional research ways, that is, doing experiments in labs. So the title of my project is Phase Field Modeling of Silver Chloride and Potassium Chloride Eutectic Growth in templates with varying geometries. This project uses a computational method called phase field model to simulate the eutectic growth and the solidification of silver chloride and potassium chloride system. So, what is phase field model? Let me first introduce sharp interface model. When we simulate the growth of the eutectic, we can choose either sharp interface model or phase field model. When using sharp interface model, the interfaces are treated as infinitely thin surface, that is, have no volume. By doing this, the interfacial location must be checked at every time step by markers. This makes meshing extremely difficult, which means it takes lots of effort building the model and simulating the process. However, by choosing phase field model, we are able to get rid of this annoying thing. Phase field model considers the interfaces to be regions with a finite volume, which is often very small. And then what we call order parameters change gradually through this region, the interface, and the value of them is from 0 to 1. So here are the material parameters of our system. The liquid slope, composition of both phases, and also partition coefficients, capillary length, and impurity diffusivity. Some Lots of parameters are listed in this table. So next is the most famous and basic model of eutectic growth. This is the Jackson-Hunt model. This equation describes the relationship between the undercooling and the laminar spacing. So delta T in this equation is the undercooling, which means there is a difference between the eutectic temperature and the temperature at the interface of the solid and the liquid. Lambda is the laminar spacing, which is the sum of widths of alpha and beta phases. M alpha is the liquid slope on the phase diagram of the alpha phase, and M beta is for the beta phase. So this system, silver chloride, is the alpha phase, and the other is the beta phase. And V is the pulling velocity. So this is the phase diagram of silver chloride and the potassium chloride system. The red lines are tangent lines of both liquid lines, from which we get the slope of them. And then this is the Jackson-Hunt curve for the system. As you can see, when the undercooling reaches its minimum, the laminar spacing is about 0.5 micrometer. So here is the phase field model I worked on. There are mainly two governing equations. The first equation describes the evolution of the phase field at every point, and the second equation is about the chemical potential of the system. With these two equations, I am able to simulate the growth of the silver chloride and the potassium chloride system. So before I actually simulate the silver chloride and the potassium chloride system, I first test the code with ion titanium system. The test is conducted in a plate with a spherical particle embedded in the middle of the domain. Okay, so after the code is verified to work properly, it is then used to simulate the silver chloride and the potassium chloride system. And here is the solidification process. So that's it. Thank you guys.